All right, so there's a reason we do this. These are all recorded. So welcome to Maths 1M Revision Seminar. My name's Nicholas Crouch. I work in the Maths Learning Centre. Let's face it, both of you know that that's a thing. I'm going to go through sort of suggested material for you guys. I'm going to actually focus on the things that might actually happen in the exam rather than the sort of questions you might have seen in the assignment, so that it's actually a little bit more directed at the exam. I will remind you that all of the seminars get put up online. So David has done hundreds. Yeah, hundreds. More than 800. David has been working for the Maths Learning Centre for more than 16 years now. And he has done sort of the order of 5 to 12 revision seminars a semester for that time. And so, yes, a lot. All of them get put up online. They would, like Maths 1M would be an example of something that would go back quite a long time, but the universities changed their system. And so we've lost some of those revision seminars from times past. Okay, so we had a list in the Maths Learning Centre, which is, so parametric curves, the fog thing, complex numbers. I'm not sure what the BE is. D is, yes. Integration, working with inverse trig functions. Actually, that was something I was going to do, and other trig stuff. So those are the things I'm going to do. You can, yes, if you do the raise hand, what I'll try and do is you guys, if you notice that Amy's raised her hand, that will be my cue to sort of check in with what's going on. Type the question, Amy, for anyone else joining online. Okay, so where would we like to start? Yeah, so trig functions is the way to go. We are recording. So we started recording a little bit late. So we're going to go 1M, and I'm going to put 11:38. All right. So sweet, everybody happy? Trig functions. Everybody love trig functions. See, this is what you guys are for. Well done. Take a bow. So I need to share the screen and share. I'm going to try and not flick back between them too much. And I'm going to remember to take my phone out of my pocket because it's just uncomfortable. Sweet. So the other cool thing we have, all right. So now there's a very small chance that you've already seen these, but this is like the sample exam from 2018, I think it was. All right, so they had 2 sample exams back in 2018, and they are probably the same exams. But they're not the ones you have are possibly the same exams, but possibly not. And so I'm going to use, so what I did with the other seminars is I've used some of the past the sample exams as a bit of a guide to the sort of questions they've asked, but not exactly explicitly what they've asked you to do. All right, so we're going to do a couple of things. All right, so we understand the unit circle for trig functions. All right, so unit circle literally means circle of radius 1. And we know that any point on there is cosine of theta, sine of theta. Literally, those are the coordinates of that point. All right, and we can actually use this to sort of help us understand what the graph looks like. You know what? I feel like what I should do is to have pretty texts. So like, oh, that looks good. So what we're going to do is if we just do cosine, I actually heard the guys talking after the last one I did about trig things. And now we're talking about how to memorize which one is which. All right, so this one is sine of x, and this one is cosine of x. So I kind of, like, I've played with this so long that these things are sort of embedded in my mind. But the advantage of thinking about the graphs like this is it's easier to see that shift nature. All right. So here we're saying the x coordinate is cosine of x and the y coordinate is sine of x. And because it's a circle, it kind of makes sense. This is the paths that they map out if I actually map them as functions. So when we're talking about these things, we go, okay. So one of the things we might get asked to do. So there's a lot of things you can remember, right? There is too much stuff to remember. So the first one is the circle inequality, circle equation. So cosine theta squared plus sine squared theta is equal to 1. That's the simplest one to remember. We can rearrange that in different ways. Sine of, I'm going to say 2 theta is equal to, so this one, so people sometimes ask me what I remember, and this is one of the ones I remember, cosine of theta. All right, see how it says that. So when I come to do sine of like a plus b, yep, good. Do also remember that I'm a bit deaf, so if you're saying something to me, you can be quite loud. So what this is going to do, this is sine theta plus sine theta. So I'm going to go sine of a cosine of b plus sine of b cosine of a. All right. So I can use my double angle formula to help me remember the addition formula. And similarly, if I do cos of 2 theta, I'm going to go, that's cosine squared theta minus sine squared theta. All right. So everybody loves sine more than cosine. All right. Think about it. It's just the way it is. So sine has the positive in it. I don't know. In my head, my brain associates sine with positive things. There's no really good reason. It's just what happens. What I needed to do with chat. So it's all there. Good. So in actual fact, the Zoom should be recording just the screenshot, the screen share, but you guys can also see the chat. And you can't really see me. I suppose I could do that if people cared, but we don't really care that much about seeing me. All right. So when I do cosine of like a plus b, I do the same thing. Cos of a, cos of b minus sine of a, sine of b. All right. Somewhere in there, there's cosine of minus theta is equal to, yep, cosine of theta, and sine of minus theta is equal to minus sine of theta. Sine is odd, cosine is even. These are literally the definition of odd and even functions. And so even is symmetric around the y-axis, odd is a rotational symmetry around the origin. If I put a pin in it, rotate it by 180 degrees, it will look the same function. And you may not believe me, but with sine, that's definitely a thing. I can hear you going, why the hell do I care, Nick? So why you care, right, is we're going to map, whenever we get asked to find sine, cos, whatever of something, we map it to an angle in the first quadrant and express it as a value in the first quadrant. So if we do this, if I do theta, sine of theta, cosine of theta, maybe I'll whack in tan of theta in the thing while I'm doing this, because tan is a thing. So I go 0, pi on 6, pi on 4, pi on pi on 3, and then pi on 2. All right. I have a plan. I do have a plan, peoples. So this starts at 0, goes to 1. This is literally square root of 1 on 4, which is equal to a half. Square root of 2 on 4, which is equal to 1 on root 2. Square root of 3 on 4, or root 3 on 2. And square root of 4 on 4. All right. Nice, easy way. That's an easy way to remember what those numbers are. These numbers are just those numbers in reverse. Root 3 on 2, 1 on root 2. Some people like to write it as a root 2 on 2. Don't care. This is a half. This is 0. 10 is this one divided by this one. And so this is going to be 1 on root 3, 1 root 3. All right. Woohoo. All right. So we've got all of these things here. I can already hear you going, but why would I want to know that? So we actually expect you to remember that. All right. So as part of Maths 1A, Maths 1M, we expect you to remember that much detail. Not a lot as far as I'm concerned. Should be fine, right? No, maybe. So okay. So why? But again, what am I doing? Where is that going? So one of our favorite pastimes is to do, I don't know, what do we feel like doing? I feel like what we should do is we should use those to do something else. So if I was to work out sine of, say, let's go 7 pi on 12. What the hell am I going to do? All right. So if I think about this really carefully, because it's a 12, I'm going to add some on 3 and some on 4. That would get me a 12. So 7 pi on 12, I reckon that's equal to pi on 3 plus pi on 4, I think. So this is going to be 4 pi plus 3 pi on 12. Slick, that's a big tick. All right. So sine of 7 pi on 12 should be equal to, and then I've carefully written out my formula, my addition, my angle sum formula. And so A is going to be pi on 3, B is going to be pi on 4. Too easy, isn't it? So this is going to be like sine of pi on 3, sine of pi on 4, plus cosine of pi on 3. It also helps if you write the right thing. So I'm going to scrub that and write it out correctly. Sine of pi on 3 cosine of pi on 4 plus sine of pi on 4 cosine of pi on 3. Okie dokie joke. What did I say sine of pi on 3 was? I said pi on 3 was root 3 on 2. Cos of that is root 2. I'm going to write it out. Yeah, no, 1 on root 2. I like that better. Plus 1 on root 2. And then cosine is a half. And so these actually have the same denominator. All right, so these both have a denominator of 2 root 2. And I'm going to have root 3 plus 1. Done. All right, so these things, yes, Rumby? No? Well, find the exact. So this would be find the exact value of. Okay, and so this is one of those things where I go, okay, sure. That's a process to step through. So if you get sort of, you know, A on 12, add, or we go subtract. Sort of, you know, N pi on 3 plus m pi on 4. So that's going to get you a 12. All right.
You can't see past where the base is, the top of the base is.
You know what, David? You know what? You know what? This trick. No, that would be it. That would be good, but also. Amusingly enough, not straight, but that's okay. Because everything is, you know, like, if you look at how most people don't like that perfectly on this page. So if I have like an A on 8 double angle formula. Double angle. I know that is one that is the university uses a program called Teams to manage the teams. Yeah, so and Chelsea Avard is my boss. And I saw her very busily trying to type something out. So that's like inevitably 5 pages of stuff for me to read. So we've got options. All right. So we're going to use an angle sum formula for something on 12. We're going to use double angle formula for something on 2, something on 8. Sorry, and we're just going to use that standard table of values. All right. That is just something we need to be able to do. Yep. Yep. They will give me all of those things. Okay. So. All right. So now there's 2 other things we do in this vein. All right. So there's the if cosine of theta is equal to, I don't know, what's a nice number? We're going to do something terrible. I reckon I'm going to go 3 on 7. No, 7. All right. I hear you say, that sounds like a brilliant plan, doesn't it? And so what is tan? 3 on 7. Tan of theta. Tan of theta. Sure. So this is not out of the question for something they do. And it's nice and simple. We're going to go back to circle formula. So we're going to go cosine squared theta plus sine squared theta is equal to 1. And so I'm going to have a 3 on 7 squared plus a squared is equal to 1. We're going to have 9 on 49 plus a squared is equal to 1. A squared is equal to 1 minus 9 on 49, which is just going to be 40 on 49. A is equal to plus or minus square root of 40 on 7. All right. I could write the 40 as, it's not going to go too far, because this is, so it's like 2 square root 10 on 7, plus or minus. So now I'd need to know more about that. And so this says quadrant 1 or 4. And so based on this would work out where, so that's actually saying, so this is saying, therefore, sine of theta is plus or minus 2 square root 10 on 7. I'd need to know which quadrant it is. All right. So, I don't know, let's say fourth quadrant. In the theta in the fourth quadrant. That would, so there would either be something that tells you about that, or it would be in the, like, so the information will be in the question. It may not be explicitly. Typically with these ones, they're fairly straight up and down and go in the fourth quadrant. But some of the other things, they've sort of left you worked it out for yourself. Yeah, sort of, they might have gone, hey, but we want theta between 0 and pi. And so that would say first or second quadrant. Oh, cosine is positive, must be in the first quadrant. All right. And so, and then tan of theta, just to finish it off, is equal to, so this bit here tells me that sine of theta is equal to minus 2 root 10 on 7. All right. That's what tells me that. And so since this is sine of theta on cosine of theta, this is going to be minus 2 root 10 on 7 divided by 3 on 7. All right, we know how to work with fractions. So minus 2 root 10 on 7. I'm dividing by this fraction, so I multiply by the reciprocal. And so I should get minus 2 root 10 on 3. Woohoo. Okay. Reasonably simple process to follow. All right. These are all sort of straightforward sort of things. And sort of we can see all of those things. So maybe what we'll do, we'll pause for a second and we'll just have a quick flick through the exam to see what the actual question was and or what the type of things they were asking in the sample exam. So set stuff, piecewise defined functions with composition. I might come back to something like that in a bit because I think that was on the list. Integrals, differential equation, more differential equation, drinks, temperature, blah, vector stuff, more weird ass vector stuff, more vector stuff. Yeah. Equation of a line. Horrible, that looks like parametric curve stuff, or can be done with parametric curves for related rates. This is, no, 1M. 1M. Haven't you? Didn't I talk to you about doing our operations? I talked to a lot of people about a lot of stuff. I might have forgotten. No, this is, so the thing is, because this is an old version of the course, this is possibly, so they didn't actually do any, so that one didn't do explicitly trig stuff. This is one of those things about exams, right? There may be stuff where they haven't actually done those things explicitly. Yeah. But I'm mildly interested in, so this stuff is actually doing vector stuff. Did you do sort of stuff like this with vectors? And so vector proof. Sure. Yeah, parametric curves. Oh, there was parametric curves. Yeah, that's good. Do more differential equations, more functions and differentiation stuff. Vector theorem. Yes, we should so do that. Woo. Picture below, complex numbers. We'll worry about that another time. Okay, so there wasn't. So trig stuff definitely does occur in there. There's one type of question that I haven't actually. So when we start talking about inverse trig functions, that's where we're sort of, that's kind of the thing I was looking for to see if there was any inverse trig. That particular set of, so that was, like I said, they're from 2018 and they don't have it. All right. So one of the questions they do in cosine of arc sine of, I don't know, Right, sine takes a number and gives you a angle. So what sort of angle do we want? I don't know. I'm going to say, let's do 7 pi on 6. Okay. Now, the actual advice is you get to have a scientific calculator. Yeah. Oh, wrong way. I need this to be, I'm going to say a half. Sorry. I need to have an angle ratio for an arc sine. And so if we just plot this out, right? 7 pi on 6 is actually sort of here. All right. Sine is negative. All right. And so this thing here will be, sorry, I want minus a half. So I'm going to have here or here, all right, for my angle. So from the minus a half, I've got here or here. And so if I do, so that means I've got arc sine of minus a half is equal to, it's going to be this one. It's actually going to be minus pi on 3, pi on 6. Okay. Yep. So when we do the inverse function, so the domain for arc sine is equal to minus pi on 2 to pi on 2. And so I'm giving my value in that region. Okay. And so that's why I'm going, well, actually, that's the one it's got to be. All right. And so, sorry. So for arc sine, it's the domain. It's the value. No, it's the range. Not at all. Too many revision seminars and too little time. Wrong brain space. So for arc sine, which is the domain for sine to have an inverse. So that's restricted domain. And so, yes. Okay, good. So the value I get out of arc sine is in that range. All right. And so the trick is, like, sometimes we do, hang on, what's this going to be? Right. So this way, I can actually just put this into my calculator and get a correct answer. And then I can interpret that in terms of the value I expect. So if I've got like a half, I expect, so cosine of, and minus pi on 6, cosine minus pi on 6, going to be equal to, that should be equal to, it should be positive, and it should be root 3 on 2. All right. So this can actually trap people with the getting it around the wrong way. So if I was to, so this, and I can just put it into my calculator because it's in the calculator, I can just do it. Literally, I heard the guys after, a couple of them were talking after the last revision seminar, and they're like, just put it into your calculator. I'm like, yes, that is, I mean, like, there is the other one where if I do it the other way, so, well, cosine, so if I do that 7 pi on 6, all right, this is going to be a negative number. So a lot of people will sort of try and, if they actually, if you do cosine of, sorry, wrong way, cos of cosine of 7 pi on 6, that's a trap. It's a trap, people. Because you're going, the sine, the arc and the cos cancel out. But this is not in the range of arc cos. So range of arc cos is equal to 0 to pi. This number outside of that. And so what I have to do is I have to work out what the equivalent value inside that region is. All right. And so, that would be equivalent to going arc cos of cosine of 7 pi on 5 pi, 5 pi on 6. All right. 7 pi on 6 here, cosine would be here, so that would be the 5 pi on 6. All right, same x value. And so that's why I do that. And then because this is in that range, I can go, that's just going to be equal to 5 pi on 6. All right. So one of the points about doing it is that having the calculator tell you what the correct answer is means that you can make sure you don't do a mistake like that. All right, that is, it's a very common thing to do, and they would, and too easy to make that mistake. So we're not gonna, we're gonna actually literally watch for it. Okay, all right, and similarly, sort of thing with this is once we've gone here, all right, cosine of that, so cosine so that's gonna be arc sine. And so I'm working out this value is going to give me -1 on minus cosine, minus √3 on 2. Okay. And when I do arc sine of that, all right, because it's giving it to me in this range here, it's going to be in the negative part. And so that's going to be equal to minus pi on 3. All right. Yep, that'll work. So it's important to sort of check where you are with these things, okay? Ideally, I should plug it into a calculator to show that the calculator will tell you the right thing. Okay, so I think what we might do is we might, anything else with the trig stuff? Yes, we are mathematicians and we work in radians, except for when we work in degrees, but we'll tell you specifically we're working in degrees if we're doing that. Like I say, quite literally the answer, like literally when I was in first year, I got told you're a mathematician, you're working radians. And then if you're an engineer, you work in degrees. Except for if you're doing both engineering and mathematics, and then, you know, good luck to you. So I had a friend who literally had maths calculator, engineering calculator, and just that was in degrees and that was in radians, and just didn't swap them. So he never made a mistake doing that sort of stuff. Okay, cool. I feel like that's, let's have a bit of a check. So that's covering the trig stuff that we're doing there. Yeah, sure. And so there are different ways to ask this type of stuff that can be quite tricky. Okay. But one of the fun ones. So the other thing we can do when we have, if we know, right, what can we do? There's a thing we can do with actual numbers. So if I know tan of theta is equal to x, find sine of theta. I know, that sucks, doesn't it just? So what I'm going to do is I'm going to go tan theta is equal to x on 1. Now, this means I can draw a triangle. Draw a triangle, peoples. A right angle triangle. Opposite, so I'm going to put in my this. I'm going to put in my theta. Opposite is x. Adjacent is 1. This is square root of 1 plus x squared. Sine theta is equal to just x on square root of 1 plus x squared. Okay. So I can get expressions for if I know that some value, I can get an expression that will work for any value of x here. All right. It's kind of what I did. So I wonder if, oh, I know what happens. My apologies to people. Come on, wake up. So the lecture theatre decided that I wasn't actually presenting anymore. And so I turned off the presentation. There we go. And that one.
Why is it making dull?
Oh, so the board is brighter. So the thing that's been projected onto the board is brighter. There's a thing. It's a thing. Are we good? And there we go. We're back. Awesome. Okay. There are any number of little tricks like this, and they can be used for doing all sorts of things. I think we've covered all the trig tricks that we need to know. One of the things, actually there's about two more things we want to say about trig formula. All right. So we remember double angle formulas, the diagonal angle formulas help us work out what the addition formulas are. If I start with my circle inequality, which I'm going to go cosine squared theta plus sine squared theta is equal to 1. And then if I divide through by cosine squared theta, I am going to get 1 plus tan squared theta is equal to sec squared theta. Nothing up my sleeve, trig formula. There are two other things that I actually remember. All right. Sine of theta is equal to sine of phi minus theta. All right. Very useful for trying other formula. And the other one is simply cosine of theta is equal to cosine of minus theta. And then adding or subtracting multiples of the period. All right. So, they're periodic functions, know the period, add or subtract the period with gay abandon. All right. The more you get used to just going, but it's periodic, I can add or subtract the period. That's going to allow you to work out these things much more easily. Okay. All right. I feel like we've had enough of trig. Sure. You know what? We're up to. Why don't we try some parametric curves? Okay, what I'm going to do is I noticed this one had a reasonable question for parametric curves. I think. So I'm going to see if I can. Going to go and check it, and I think we might sort of talk about what they're doing there. So, there is a lot of material that we've already gone through in this, like in revision seminars. Not this one. Ooh, which I love it when we have a plan and the plan doesn't work. All right, not that one. What's that? So parametric curve is just saying, so I can have a curve in many dimensions and it can have a parameter. And so it's like a path in sort of more dimensions than just one. All right. And so that other parameter, that parameter sort of tells me where I'm up to. So in actual fact, one of the things we do when we're talking about, we quite often want to parameterize a function. All right. So there is actually a thing here where it's here somewhere. All right. This is an example of, it's not actually strictly speaking parametric and parametric curves. One car is traveling due north due north of an intersection and traveling away at 60 kilometers an hour. Another car is 10 kilometers east of the intersection and traveling towards the intersection 80 kilometers an hour. What is the rate of change? All right. Find the Cartesian form. Okay, so this has got, so in actual fact, let's draw the picture. Let's give ourselves a little bit more space. Draw the picture. All right, so we're going, one is 5 kilometers, so that's 5 kilometers. And he is traveling to of an intersection and traveling away from it. So he's going that way at 60 kilometers per hour. And the other one is 10 kilometers to east. So that's 10. And he is traveling that way at, what is 80 kilometers an hour. So we do A, B. So I can actually write A as a parametric curve. So it would be like 0 and then 5 plus 60t. All right. I can just go, I'm 5 kilometers away, I'm traveling at 60 kilometers an hour. And so t in hours. Okay. And I can do the same thing for B. Okay. So B is going to be, so he's 10 minus 80t and 0. Okay. So I can create my parametric curves for this. Now, if I want to talk about what is the rate of change of the distance between the two cars at that instant. All right. So what I can do is I can create a formula for this. All right. So I know that when I talk about this difference, this minus this, or whichever way I want to do it, I can actually get, so if I do B minus A, that's the distance between them as a function. And so that is actually a vector. So if I'm doing B minus A, it's going to be 10 minus 80t, and minus 5 minus 60t. Okay? That is like the vector that's between them. All right? So literally at this point, I go this in here. And so if I want to talk about the rate, so what is the question said? What is the rate of change of the distance between them? I want to go, well, the distance between them as opposed to the vector. So I actually want to do the length of the vector between them. And so that should be like square root of, and then 10 minus 60t plus minus 5 minus 80. Nope, that should be 80. That's the 80 and that's the 60. Good. Got it right that time and forgot my squared. Awesome. Okay, so that's my actual function. I don't really want to expand that out. All right. And I'm allowed to just go, no, not going to. So I want to find the derivative of this thing. Sound like a thing? Yes, otherwise yeah. So if I do the derivative with respect to t of the distance, this is going to be horrible chain rules. This is one function. So some function to the power half. So chain rule says it's going to be 1 on that function. 1 on 2 times that function. And so 10 minus 80t all squared plus minus 5 minus 60t all squared times by the derivative of the bit inside. All right, and so that's going to be 2 times 10 minus 80t times by minus 80 plus 2 times minus 5 minus 60t times by minus 60. Bleh. I'm going to try and simplify this a little bit. All of this is going to go on top. All right. So it's going to suck. Those people playing at home, going to suck. All right. But it is just messy algebra. Okay. So I'm going to have myself minus 116, that times that, by 10 minus 80 t, minus 120, minus 5, minus 60 t, all on 2 times the square root of this crap. 10 minus 80 t all squared, plus minus 5 minus 60 t all squared. I want to know this value when t is equal to 0. T is equal to 0. So d by dt of my distance, t is equal to 0. Sometimes when we put this line and the little t is equal to 0, that's just saying we're going to evaluate when t is equal to 0. And so I'm going to get minus 160, t is equal to 0, so that number is 10. Minus 120, t is equal to 0, so that number is minus 5. Woohoo, number. And so this is 2 square root of 10 squared plus minus 5 squared. Blah. Let's push it up. Sweet. 1,600 plus 600. 2 square root 100 plus 25 is going to be equal to 1,000 on 2 times 5. Sorry. Thank you. Times square root of 5, which we are going to be able to go, that's 10, so I'm going to go minus 100 on square root of 5. 50-ish kilometers an hour. I could, it's conceivable that I could have asked, you know, sorry? Oh, 2 times.
Oh, that's time, okay.
Yep. Yes. 2 times 5. So that's, yep. So in actual fact, these cars are getting closer together, if you like. And I could ask, how long will it be before, well, what time are they at their closest, or something like that. So wouldn't do it for 1B because that's too complicated. But you know, yeah. Sorry, 1M. Yeah, way too complicated for 1M. Okay, now the other part about this, so I'm going to flick to the next one because they've got a different one, which is a little bit more what they. So that kind of fun, messy algebra. Nobody loved it very much. Okay, so where are we up to? 1M5. The other question they had sort of was x of t, y of t is equal to cosine of t sine squared t. I feel like this was used in an assignment. This, yeah. All right. Or find the Cartesian form of the parametric curve. Ugh. This is one of those horrible things where we're going, hang on, I want to go from this parametric form to a Cartesian form. And so what I can do, I want to exploit something that says like cosine squared t plus sine squared t is equal to 1. I want to have that relationship. This one's actually surprisingly easy, all right? And one of the things that happens in exams is that we're going to do questions that are, from the point of view of what you did in the assignments, quite easy. Because in the exam, firstly, you don't have anything to refer to, so you haven't got your notes or something to refer to. So the actual thing we're asking you is, do you remember what sort of thing you were supposed to do in this situation? All right. So I don't necessarily need complicated steps. I need to know what the right thing to do is. And so these are both trig functions. All right. If they weren't, my life would be unpleasant. But it does mean that I've got some sort of equation. And so this is going to get me x squared. So x squared plus y is equal to 1. And so I can really simply write this as y is equal to 1 minus x squared. And so I've got an explicit form of the equation. Because see how y is sine squared? And so, yeah. So it's really making sure we pay attention to what we said. Okay? Now let's bring them both down a little bit because can't quite do that. I can. Okay, so I can do that nice and easy. All right, and that's one of those simple things that we do with parametric curves. For those of you doing engineering, parametric curves are actually really useful for calculating integrals in higher dimensions. So if I'm doing sort of volume, surface area, whatever integrals, then I want to parameterize a curve to make the integration that I'm going to do nice and easy. So, and so I can, quite often they're straight lines or they're sort of like a spiral. I can do like a helix spiral type of thing in a parametric way relatively easily. I say relatively easily, not easily, relatively easily. Okay, so cool. Okay, so how are we feeling? So I've still got things like the Folger thing, so the composition of functions. I wonder if I had something nice in the composition of functions. I don't feel like we did. Composition of functions. So we actually, where you are at the moment with this sort of stuff is we should know about composition of functions, but when we're talking about composition of functions, actually the thing we want to know is how to pull it apart. All right. So when I'm going, I'm going to use the idea of composition of functions to help pull things apart so that I can do the differentiation more easily. So that's why we're going to do, so that's why we're interested in composition of functions more than the actual thing. That's not going to do it. That's not going to do it. So this method's not going to do that. So I might see if I can find a way to sort of work it into something else. Maybe. Actually, this will possibly be, if we talk about what's happening here. Yes. The air conditioning may have decided to turn itself off. You found the button? Oh, there's sometimes in these places, then you have to wake the air conditioning up. So there's that panel on the wall. There we go. We are going. Or is that the lights? Yes. If it's getting a bit stuffy, just. Okay. Oh, good. Yeah. No, that's good. No, I'm comfortable. I'm just worried about you guys because I sometimes forget. That's the lights. That's one. Good work. So the reason I want to talk about these ones, I'm going to copy this information out as we go, is because this piecewise function is actually, it's going to mess with our heads a little bit. All right. So it actually, like doing composition of functions like this is actually a lot harder than it looks. But it is still a relatively simple process. And so we should be able to do it relatively simply. This pen doesn't like drawing lines. Okay, so we want to do, so if we just think about trying to find f of g of x. So, literally, this will work out to be 0 if, and so g of x less than 0, and 1 if g of x greater than or equal to 0. All right, now, everybody's favorite pastime, when is g of x greater than 0? So if we were to just quickly sort of do a little sketch here of the side, all right, so this bit here is for x less than 1, g of x is equal to x. And so that's this bit. It's a straight line from here. And x squared actually goes from in there and goes up. All right. So this actually is going to change a little bit. So when it's less than 0, so this is going to be equal to 0. And I'm going to interpret this when x less than 0. All right. And it's going to be equal to 1. So you notice x greater than or equal to 0. Greater than one, that's right. Good. Check. And so this actually, amusingly enough, because g maintained the sign of x, all right? So the way we've expressed g, we maintain the sign of x. It didn't actually change it, f at all. Like f didn't change when I did the composition with g. So kind of interesting. The other thing they asked us to do, and so the question actually asked for f of g of 0. If I do, so f of g of 0 is going to be f of 0, which will actually be equal to 1. Ooh. All right, so that's what we got there. The next one, bleh, I'm going to write this in here. So this would be difficult. So the next one said, so this is g of a half plus f of a half. Bleh. So this one we can do as a function. We don't have to. I wanted to sort of do that thing where I go, hey, let's map what happened by putting g actually inside and then seeing what actually happened. All right. This one, way more complicated. I'm not even going to try and do this. I am going to go back to, I'm going to do something else in a second. If I look at g of a half is less than 1, so I'm doing x. So we're going to do g of, and this is just going to be a half. And when I do f of a half, that's greater than 0, so this is going to be plus 1. And so I'm going to write that as g of 3 on 2. Now I've got g where x is greater than 1, and so this is going to be 3 on 2 all squared, 9 on 4. So it's not actually a difficult thing to calculate. I don't want to try and work out an arbitrary formula for this. But I do want to try and do the same, do a bit of playing with these two things here. If I was to do the composition of g of f of x, not going to be very much fun. It's going to be very simple, isn't it? So this would be equal to, it would be f of x if f of x is less than 1. And it will be f of x squared if f of x greater than or equal to 1. F of x is either 0 or 1. So this is equivalently saying it's equal to 0 if x is less than 0. It's equal to 1 squared if x is greater than or equal to 0. Again, just by working out what it is, I've got a nice simple formula. All right. I kind of want to mess with it, but also I'm not sure it's going to add value to the process. So I'm going to let that go there. Okay, so exam questions are not necessarily ridiculously tricky. All right, it's about understanding what the process is. Yep, so it is actually interpreting what they're asking correctly. And that can be a very difficult thing. Possibly what we'll do, so those are piecewise functions. So there is the sort of more, like I could go, I could have f of x is equal to, I don't know, x squared plus x plus 7. And g of x is equal to e to the minus x. All right. And so if I do f composed of g of x, literally I can write this as g of x squared plus g of x plus 7. All right. I can just, that's literally what that statement means. And so I can then just work out what that is. E to the minus x squared plus e to the minus x plus 7. This is a bit of a trick. E to the minus 2x plus e to the minus x plus 7. The reason this is interesting is I can go backwards on that. I can actually take that and split it up like that. From the point of view of doing a derivative, this can help me actually understand it. Or quite often when I get an equation like this, I actually go, I can solve that quadratic and then interpret what that result would be in terms of e to the x. All right. So if I'm solving that equation, that's actually quite hard. But what I would do is I would solve this equation. So if I have x squared plus x plus 7 equal to 0, say, then I'm going to go my quadratic formula. X is equal to minus 1 plus or minus square root 1 minus 4 times 1 times 7. Going to be complex. That's a problem for me. On 2. All right. Is equal to minus a half plus or minus square root minus 28 minus 27. Complex numbers. Woohoo, can't do anything more. All right, let's try again. X squared plus x. So if I have e to the minus 2x plus e to the minus x plus 7 plus 7 is equal to 0, it's not going to happen. So I'm going to say 10. All right, and that's going to get me x squared plus x minus 3 is equal to 0. All right, I need to make sure my quadratic actually has some solutions, some real solutions. Complex solutions, I could have pushed it into the complex plane. I could have done a horrible thing. You don't know about that yet, or you're not supposed to. So we're not going to do this. So I can just do the quadratic formula again. X is equal to minus 1 plus. This is me. Well, because this equation, because this is positive and this is positive, the minimum value for this particular expression is actually 7. This value can't achieve a value of 7 or less. So I've chosen a value greater than 7. Just the way it's written. This This will definitely pass through any value greater than 7.
Oh, yeah.
Yep. Follow me? Yep, good. No, that's okay. But what I've done is I've gone, oh, okay, that's interesting, but also not helping my point, so I'm not going to do it that way. So -1 on 2 plus or minus, and this is now 12 plus 1 is 13, square root of 13 on 2. Therefore, x is equal to -1/2 on 2 plus root 13 on 2. Or e to the minus x is equal to -1 on 2 plus square root of 13 on 2. I can't have the negative here. So one of the tricks with doing this is because I'm going to go e to the x is equal to this thing, I can't have a negative value for this thing. There is a negative root, but it can't, that one won't give me a solution. So this is the one I have to use. And that will give me a value of x. I'm not going to bother doing that because that's tedious and time consuming and not helpful. So there is things about the composition that help me when I recognize a function. So when I recognize that composition of functions, I can use that composition of functions to help break down. And that's actually the real thing that we want you to understand about composition of functions. Where we are at the moment, it's about making sure you understand how to do it and how we want you to understand how to do it so you understand how to undo it. Okay? That was the plan. Always the plan. Okay? So that's what's going on with that sort of thing. I think we might let that go at that though. So differential equations and integration. Sure. I don't know. What have we got? What have we got? Oh, I had this, was it this one? There's one. Oh, there was. They have this. Yeah. So if I look at this integral ln of x to the power 5 on x dx. 1, 3. Now, if we actually read the question tells me what the u substitution is. All right. So when we're doing a substitution, when we have something like this, I'm either going to go one or two ways, integration by parts or integration by substitution. All right. I'm going to go, hey, there's a trick. All right. So this is a special case. Normally I go, hey, the problem is at the denominator. So I set the u to be the denominator. In this case, that's x. And so I don't want to do this. But I kind of also know that if I made u equal to ln of x, then the derivative would involve that. So I'm going to go u is equal to ln of x. Sorry. So not always. For something like this, where it's a non-trivial decision, they're going to do that because they want to see you do the substitution, not necessarily pick the right substitution. Okay? So they will do, it is completely conceivable that they will get you to do something where they don't tell you what that is. Completely conceivable. Yeah. So, you know, it's a possibility. And so if I'm going to do du on dx is equal to 1 on x. And so this allows me to go, oh, this is the thing that's going to do this. My du is equal to dx on x. So when I write this out, my integral is going to be u to the power 5. And this x on dx bit is just going to become du. And that allows me to go, all right, add 1 to, so u, add 1 to the power, divide by the new power is going to be what my integral is. And so this is like, here, this is x is equal to. These are values in terms of x. All right. And so I could leave them in terms of x. All right. And so this would be evaluate when x is equal to 1 and x is equal to 3. But then I'd want to transform this back into, so this would be like ln of x on 6 to the power 6. X is equal to 3, x is equal to 1. And so it's going to be ln of 3 cubed on 6 minus ln of 1 on 6 power 6. Make sure I write the right number. ln of 3 power 6 on 6. This number is 0. ln of 0, ln of 1 is 0. Okay, so this would be my answer. Okay, that's simple. Yeah, I mean, like, technically that's an exact value. Technically, but you could shove it into your calculator and go, hey, I know ln of 3 is slightly more than 1, so when I took the 6th power of it, who knows if it's going, it's like 1.1, so it's like about 1.6, and so when I divide by 6, it's going to be 0.2 point something or other. Not necessarily a big number. 1 n 7. So the other thing they do, I wonder if this will work. I saw this. All right. So we want to do this by integration by parts. Yeah. Well, we don't want to do it by integration by.
Oh, because when you take away okay.
Yep, good. That's okay. The whole point about being here now is you get a chance to ask me questions if something doesn't make sense or if there's something you want me to talk about more. What's that? Yeah, so if I do ln of 3, it's going to be, so if I actually put it into my calculator or whatever, I will actually get an actual number. So if I do this, I actually use Excel to do my calculations equal to ln 3. Okay, sure. And so, genius, thanks. So seeing how that's just slightly less than 1.1. All right. Number really doesn't make a lot of difference. Sorry for the people playing at home, because didn't actually transfer the screen. So with this one here, so what I actually do when I work out the integration by parts rule is I do this, right? And then I go, I'm going to put a dash on the G here, which means that dash goes on the F here. All right. It is, these two have to be, the dash is on one of them and they have to be on opposite ones. All right. And so it doesn't matter. I don't like to use the G and the V and the U and the V because with my handwriting, they look almost identical. And so that sucks. So that's why I want to separate them. I want to go, so I can differentiate ln. So I want to go f is going to be equal to ln of x, because if I could integrate ln of x, I wouldn't need the integration by part thing. So now I'm going to go, so f dashed is equal to 1 on x, and so g dashed of x is going to be equal to x cubed, and so g is going to be, and so I have to integrate, and there. Some people sometimes ask me if I could put a constant of integration there. Yes, I could, but it's not going to make a difference to the answer, so I'm not going to bother. All right, that's one of those tricks. We don't need it there. I'm not going to do it. So now rewrite my integral. So x cubed ln of x, and integration by parts is rewriting the integral. Not solving the integral, it's rewriting the integral. And so it should be these two. So the actual integral is these two. And so FG, that one. And so the bit that goes in the second integral is that second line. So it's like 1 on x and then x to the 4 on 4 with respect to x. And so now I do a little bit. I tend to like to put stuff in front of the ln of x, so we don't mistakenly put that inside the ln of x. And then my integral. So this x cancels with one of these here, so x cubed on 4 dx. And so when I write this out, x to the 4 on 4 ln of x minus 1 on 4, and then x to the 4 on 4 plus c. If I wanted to go further than that, I've actually noticed there's an x to the 4 on 4 in both of these, so x to the 4 on 4, and I would have ln of x minus a quarter plus c. I could factorize. I'm a huge fan of factorizing when you can, so that's always a great way to go. Yes, Rumby. No, well, yes, I rewrote the integral, and then I had to do this integral to solve the original question. Yeah, so, yep. So that integral is just that. I've really taken a factor of a quarter out the front, then integrated x cubed to give me x to the 4 on 4. That's why I've written it that way. That's okay. Okay, sure. Cool things with integration. So, there's going to be, sure, where are we up to? What next on my list? Complex numbers. Okay, I might, no, actually I wanted to do differential equation. What sort of D did we have in this exam? So there are some things, right, you will get regardless of what you know, the exam. There will be a differential equation in the exam. Believe. That's got a simple one. Generally speaking, differential equations. So you're gonna get a separable differential equation, or did you do logistic differential equations? Did you do logistic differential equations? Yep. If you didn't hear about it, you didn't do it. Oh, hey, this is what's that? Oh, Disco Stew loves the Newton's calling, but I don't think he's written the exam for 1M this time around. I think 1M is the responsibility Adrian Kerber. And so this sample exam had this differential equation. E minus x on y squared. So you didn't learn a lot of different types of differential equations, okay? So you're not going to get many different forms, okay? And this is going to be one of them. So this means it's going to be separable. All right. And so you are going to go, I'm going to have y squared dy on dx is equal to e to the minus x. I'm going to rewrite that as y squared dy is equal to e to the minus x dx. And then, hey presto, whack an integral sign in there and do this. All right, so I'm going to get y cubed on 3 is equal to minus e to the minus x plus c. We should be used to the idea now that even though I've got an integral on both sides, I'm only going to use one constant of integration, because if I had C1 here and C2 here, I'd put them over to one side to make them sort of C1 minus C2 or whatever. And so it's going to be nice and easy to do that way. If I want an expression for y by itself, I'm going to go minus 3 e to the minus x. So depending on what I want, I can sort of do 3c or just c. Because I haven't used the initial condition, did I have an initial condition? Yes, I did. I got told that y of 0 is equal to minus 1. So I could go minus 1 cubed is equal to minus 3e to the power 0 plus c. This is going to be minus 1 is equal to minus 3 plus c. Therefore, C is equal to 2. And so I'm going to have y cubed is equal to. Now, the reason I'm doing this now, and it doesn't actually matter as long as you do it at that step and then you put it in at that spot. So I'm going to go minus 3e to the minus x plus 2. And so I'm going to go y is equal to q root of minus 3e to the minus x plus 2. That will be my solution. All right. Doesn't matter where, if I get down to the final bit and then I work out what C is, or if I do it at the start, once I've got this expression, sorry, I can put in the value there and work out what C is and then carry it through. It kind of doesn't matter. There is some things about the way we write this that we might not want to do otherwise. Okay. So it can definitely happen one or two ways. What? So the reason, so I'm actually going to try and quickly whack in some Euler's method. All right. So they've gone, hey, this is my expression. All right. So we want to go, the question literally says, use the Euler's method to find E1. 2 steps. So notice 2 steps. So we have dy on dx is equal to, where was the thing? E to the minus x on y squared. All right. And we had y naught is equal to minus 1. So we're going to set up a table. We're going to have like an x, we're going to have a y, we're going to have a dy on dx, and we're going to have a h times dy on dx, which is, I'm going to call change in y. All right. Cool. Don't need that much, but anyway. So initial values, x is equal to 0, y is equal to minus 1. This is going to, so when I put in 0 and minus 1, so this is going to be 1. And we should have done, I need to get a distance of 1 in 2 steps. And so that's going to be h is equal to that. All right. And so when we do this, this is going to be a half. So this is going to be, what goes here is like this number plus h. So it's going to be 0 plus a half is equal to a half. This is going to be this. So this is going to be y plus change in y from above. So it's minus 1 plus a half. And so that's equal to minus a half. All right, slick. Now, this calculation is going to suck a little bit. So e to the minus a half divided by minus a half squared. This is going to work out to be 4. So if I'm dividing by a quarter, I'm timesing by 4. And so I'm actually just going to write this as e to the minus a half times by 4. And so this is going to be 2e to the minus a half. So when I come down to here, this should be a half plus h, which will be equal to 1. And this should be minus a half plus 2e to the minus a half. All right, so my y of 1 is approximately equal to minus a half plus 2e to the minus a half. All right, that's an exact value. Again, if I wanted to, I could actually bust out the calculator and work out what that number is. Okay. Method, what we're looking for is something like this in the table. Different lecturers do it slightly differently. I've actually deliberately calculated, so h is how much x changes by. I've deliberately written a column specifically for how much y changes by, because the amount y changes by is h times the derivative, the x step times the slope, and that's going to make it nice and easy for what we're going to do. Okay, sound like a thing? Sweet. And so that, and if you look, I mean, like, that wasn't very hard. It's only worth 2 marks according to this, but like there is a little bit of this is me going, and so this thing here, they tried to organize it so there were 70 marks in 120 minutes. So each mark is worth about about 2 minutes, a little bit under. And so that's like 4 minutes supposed to be working. And I've explained it to you and done it in that same time, in less than that time. It's not a difficult thing, but you've got to remember Euler's method, draw out my table, make sure I work the trick. There was only really one trick, and that's working out the H step. And that's not hard, but it's implicitly stated, not explicitly stated in the question. So the way the question worded was find an approximation for y of 1 when I've given you y of 0 is equal to -1. So it's making it a little bit, making you think about what it means. But it did specifically say 2 steps. All right. Similar sort of thing happened with upper and lower sums. All right. And they upper and lower sums for approximation of integrals. Didn't you guys do upper and lower sums? You always do upper and lower. Didn't you? Upper and lower sums for integrations. Didn't you? Okay. I always thought that was in 1M. Possibly, you know, my bad. Okay. So we're getting down to we're firstly running out of time, and secondly, getting down to complex numbers. Okay, let's find me some complex numbers. So the first thing I'm going to do about complex numbers, so you notice I'm writing the time as well, so that what's going to happen is we can actually put in a timestamp. So we can actually, what's that?
I'm going to pick those papers.
Oh, so I'm going to scan them and put them up online with the recording. But no, you can get them after I've scanned. All right. So yes. So the working will go up online with the seminar itself, but having those times will help me sort of put a little bit of a, hey, when did I start talking about things? Okay, first thing we're going to go De Moivre's theorem. De Moivre's. I can't remember how to spell it, which is like z is equal to r cis theta, then z to the n is r to the n cis n theta. Okay, we love this thing. How much do we love this thing? Yes, a bit more than that. Because, so I hear you go, Nick, all those trig formulas are way, way difficult to remember. Why would it, how am I going to do that? And the answer is you are going to go to Moivre's theorem. Have you ever thought about this? If I was to take, so if I go z cubed, right? That would be cosine of theta plus I sine of theta whole cubed. But De Moivre's theorem tells me that that's going to be cosine of 3 theta plus I sine of 3 theta. Yeah, I know. You're going, that doesn't look like. Yep, just so I've made R1 and I've sort of dropped this over this way. And so when I'm actually, if I want to expand this out, I'm going to get myself cosine cubed theta plus I, I'm going to say cosine, that should be cosine, people. Cosine squared theta times sine theta. I've taken the I out the front, and I should have put a 3 here. Plus 3 cosine of theta sine squared theta I squared. All right. The reason I want to do that is I want to make sure that I get I sine of theta cubed. So that's going to become a -1. So when I'm going to go, those are real components. So I'm going to have cosine cubed theta plus 3 cosine of theta minus, forgot my I squared. sine squared theta plus I by this term, 3 cosine squared theta sine theta plus sine theta cubed. So when I did the I cubed, I squared became -1, so that became minus I, but the extra minus made it plus. Okay? Now, but the Moivre's theorem is telling me that cosine of 3 theta, that's the real part. So that's equal to cosine cubed theta minus 3 cosine of theta sine squared theta, and sine of 3 theta is equal to 3 cosine squared theta sine of theta plus sine cubed theta. I can use the Moivre's theorem to...
Are you going to show us how this one?
Yes, and also that I can use it to create a formula if I want to. So specifically my angle addition formula or my double angle formula, I can use the Moivre's theorem to work out. And we should be quite clear, because my brain is terrible and I forget things when I get under pressure. When the first year maths exam, I did literally that to work out the addition formula, the angle, the cosine of 2 theta and the sine of 2 theta. Literally did that in the exam because I couldn't remember what I was doing. All right. So you can do it. You have a plan. There is a plan. We don't have to worry about it. Okay. All right. So that is a thing I can do. So the next favorite part. So there is always, let's file through the thing. Am I doing this to show you? Yes, in some respects I am. So we're going to try and find what horrible things I did with complex numbers. Do horrible things with complex numbers directly from a sample exam. No. No. Oh, that's what you want to see, isn't it? We want to go z plus 2i z conjugate is equal to minus 5i. Z in set of complex numbers. Sure. This is just, so this is where just algebra. All right, so we're just going to believe that we can do the algebra thing. And so we're going to go z is equal to a plus bi. So I'm going to a plus bi plus 2i by a minus bi is equal to minus 5i. So a plus bi, this is going to be plus 2ai. And then, so this is going to be minus 2bi squared is equal to minus 5i. That really became minus 1. So my real part is a plus 2b, and my imaginary part is b plus 2a is equal to minus 5i. So a plus 2b is equal to 0. And b plus 2a is equal to minus 5. Choose your favorite method for working out what stuff is. So a is equal to 2b, And so b plus 2 by 2b is equal to, yes. Yes, yes, it is. And so we've got b minus 4b is minus 3b, minus 3b is equal to minus 5, b is equal to minus 5 on 3, which is equal to minus 3, which is equal to just 5 on 3, or 1 and 2 on 3, doesn't really matter. And so a is equal to minus 10 on 3. It's a complex number. Okay, sure. Woohoo, everybody happy. All right.
The idea of that person is to find out what they.
Yep. Ooh. So, yeah. So, this one has a fun question. Fun question. Fun question for complex numbers. So if we have root 3 minus I to the power n, all right, what do I have to do? All right, so first thing is I'm going to convert this to a complex, to a polar form. So if I take z, which is equal to root 3 minus I, root 3 minus I. All right, so length of z is equal to square root of root 3 squared plus minus 1 squared, which is equal to square root of 3 plus 1, square root of 4 is equal to 2. Yay, 2. Good number. Everybody loving that number. And my theta. So there's a thing where I go the complex bit divided by the, so minus 1 divided by that. So this is going to tell me, so this is like tan theta is equal to that. And so that's saying theta is equal to minus pi on 6. And that feels about right for my little diagram. Every time I'm converting a number to polar form, I do my little diagram to make it easier for me to see what I'm doing, and then thing just falls out, right? Great, love the plan. So, bleh. Right, so what I need, so z to the n is going to be 2 to the n cis n minus pi on 6, which we might write as 2 to the n cis minus n pi on 6. Ideally, it's actually a bit of a trick. So if we think about what's going to happen, first quadrant, the thing is 0. Here it's like pi. Here it's 2 pi. It's actually some integer multiple of pi. And so the first n for which this happens, so we're assuming n is not equal to 0, so therefore n is equal to 6. All right. So if n is equal to 6, we would be getting 2 to the power 6 cis of minus pi, which would be equal to 2 to the power 6 is like 64. Feel like that's the thing. Otherwise, you can say yes. 64. And this is going to get me minus 1. So minus 64, which is a real number. And it would be the first of the real numbers. So, sorry? Yeah. So that was actually worth 3 marks. And this bit here where we actually recognize, so one of those marks is just for putting in, finding polar form for Z. One of those marks is just applying de Moivre's theorem correctly. And so if you do that and don't do that last bit where you actually work out what the answer is, you've still got 2 out of 3 marks, right? It's really important to go do the thing you can. If you don't know what that final answer is, you can still get most of the marks by doing the obvious things. De Moivre's theorem, I have to write that thing in polar form. I know what de Moivre's theorem is. I will just write out what that implies for this question. And then once I've done that much, I go, oh, actually, maybe I can do this in here to work out what's happened. Okay, so I can actually get more out of this by working out what the thing is, what I can do with this thing. All right. So how are we feeling? All right.
Is there a real number that jump line you get how you suddenly just say, oh, it's a real number, it's some multiple of mine.
So because I needed, yeah, so because with my n times pi on 6 or minus pi on 6, I know like if the angle is equivalent to either 0 or pi, sort of plus or minus, plus some integer multiple of 2 pi, then that would be all right. So 0 plus 2 pi is going to give me 2 pi, 4 pi, 6 pi, whatever. If I'm over here at pi in the negative region, then it's going to be sort of pi, so minus pi plus 2 pi, so pi minus pi to pi, 3 pi, 5 pi, 7 pi. And so it's always going to be just some multiple of, so I kind of had to undo the fraction part. All right. And so the way that does that is it sort of, so if I'd taken this thing here, it's going to be a little scrappy, but if I'd taken my minus n pi and said that's 6m pi, then the smallest value of m I can have would be 1, and that would mean n would have to be like minus 6, or correspondingly plus 6. I could make this minus 1, and that would mean n is plus 6. So I could have used did it say all right, because it asked for the smaller, the question actually asked for the smallest. I could have used like 60, for example. That would have been a lot less fun. But it would have still been incorrect. It would still be a correct answer. I think, did it actually say smallest? Yeah, no, I did actually specify the smallest n. So that's why I chose that. And did it say positive or negative? Oh, smallest n greater than 1. All right, so that's why I couldn't use 0 too, right? Because it had specified smallest number greater than 1. That's why I went with 6 as opposed to say minus 6 or 12. 12 would have been another option that would have given me that, like if n was 12, that would have been 2 pi or minus 2 pi. That would have been fine. Would have been an integer, but it still would have been a real number and an integer, in fact. But it wouldn't, it's not the smallest one that would give me an integer, okay? Or a real number, okay? Sweet. I mean, like, I feel like I've covered most of the things people have talked about here. I'm just going to quickly Actually, I'm just going to quickly check to see if there wasn't other questions in the Maths Learning Centre folder that got emailed through Maths Learning inbox. The tables, HMS. No, nothing there. Okay, beautiful. So I think I might actually finish a little bit early here. Nice work, guys. Thank you for coming along. Thank you, Amy, for being online. I think we're going to call it a day at this. Thank you, everyone, for your attention. This seminar with these sheets, with what I've written as I've worked along, will appear online probably tonight. David's fairly good at putting these things up online pretty much as soon as I do them. But yeah, hashtag I may have stuffed something up with a recording, but it should be all right. So thank you very much. I will see you in the Drop-in Centre, Maths Learning Centre, open until Friday, 10 a.m. to 4 p.m. From next week, we'll go to 1 p.m. to 4 p.m. But that's because most of you will have done, I don't know when the Maths 1 exam, Maths 1M exam is, but
Thursday or Friday for last week.
oh, so we'll be seeing a lot of you guys.
Thursday.
Okay, sure. Yep.
At 1 p.m.
Sure, cool. Well, don't rely on us. Make sure you look it up for yourself. That is the key message to take away. Thanks, Rumby. Thanks, Grant. Sure. You know the deal. You know where to find us. See you.
Yeah. This whole week is just maths studying.
Yep. Do this. Stop sharing. See you over there.